All right. Well, thank you for the kind introduction, Chris. We appreciate you and your team helping us make this webinar and even the past few happen. I am grateful to introduce Robbie Pickering. Robbie is an environmental engineer with more than 14 years of experience promoting water efficiency and sustainable facility management. In particular, for WaterSense, he supports the product and home specification development process and has helped develop technical materials to assist a variety of commercial, institutional, and multifamily building types in understanding and implementing water-saving best management practices. You've probably seen him on several webinars in the past, so it's great to have him back for this particular topic. Also joining us to provide some real-world savings results from mechanical and other projects is Scott Riley from the St. Joseph's Healthcare System in New Jersey. Scott is the Director of Maintenance and Engineering and will be sharing how they were able to substantially reduce water use across two of their campuses. So I say this at every webinar, but our webinars are part of a monthly series that Energy Star and WaterSense co-host to encourage water efficiency within commercial and institutional facilities. Already this year, we've held 5 webinars which covered how small operations and maintenance changes can save you water, how to go beyond that low-hanging fruit and take on retrofit or replacement projects, how to conduct a water assessment so when you're really starting from square one, how to reduce outdoor water use and tackle landscape transformations, and most recently, how to update restrooms to save water. Recordings of these webinars are available on the Energy Star website if you're interested. And after today, coming up this fall, we still have 2 more webinars where we plan to dig into how to use Portfolio Manager to understand facility water use intensity and how to use advanced metering technology, AMI, to improve water management and detect leaks. Please be on the lookout for those invitations to sign up for those webinars. Lastly, I know for a fact there are great innovative water saving stories out there. If you'd like to go from being an audience member to a speaker, please reach out. We'd love to hear it. We're actively recruiting and we're planning for our webinars in 2025. And your engagement in WaterSense brings value to everyone. One more thing, our team will be at the WaterSmart Innovations Conference in Vegas next week. It's like a fairly big water event. If you're going to be there, we'd love to meet you in person. Stop by our booth, and I'll drop my email in the chat so we can all connect. So just some run of the show. After some WaterSense basics, we plan to focus primarily on water use within cooling towers, but we'll also touch on best practices associated with single pass cooling. And then we have the case study from St. Joseph's Healthcare System. So just in case we have some new folks tuning in fact, hopefully we do have some new folks. That is the goal. WaterSense is a voluntary program that was launched by EPA in '06. The program works to promote water efficiency so that we can help organizations and consumers save water for future generations. I know for my age group, a lot of my friends are having kids, are young kids now. So please know that your work is personal and it's meaningful. The WaterSense label, which you can see here, provides a simple way for consumers and businesses to identify water efficient products, programs, practices, and homes. And products that earn the WaterSense label have been independently certified for water efficiency as well as performance. The label is reserved for products that reduce water use by at least 20% and again, perform as well or better than kind of the standard models that are out there. So there is a wide variety of residential and commercial products eligible for the WaterSense label that can be used in commercial and institutional facilities. To date, over 45,000 product models have earned the WaterSense label in 8 different categories, spanning indoor plumbing products, toilets, urinal, shower heads, lavatory faucets, and irrigation products like irrigation controllers and spray sprinkler bodies. Again, more information on how each of these products can save you and your facility water is available on our website. Again, we're happy to answer any questions. Um, we also work closely with our Energy Star colleagues here in the building to include water factors in their specifications. And conversely, we consider energy savings in ours. For example, Energy Star certified clothes washers, dishwashers, ice machines, and combination ovens are all also water efficient compared to standard models. So right now, I'm going to go ahead and turn it over to Robbie to really dive into information on why and how to reduce water use in mechanical systems.
Thanks so much, Kirsty. Yeah, while I get analyst status. There we go. Perfect.
I think you got it.
So yeah, I'm gonna jump right in since there's a lot of information to cover and we have a great case study ahead. So I'm just gonna kind of dive right in. So within commercial buildings, water use varies depending on your building type. Knowing exactly how your building uses water and where it consumes the most will really help you prioritize your focus and look for potential efficiency opportunities. This can be done by tracking water meters or sub-meters or conducting a more detailed water assessment and developing a water balance. We don't really have time to talk about a lot of those topics today, but if you're interested in those topics, we have our previous Water Wednesdays webinars that Kirsty mentioned, and a variety of resources that I'll share towards the end of this presentation to talk about how to evaluate your own building's water use. But the chart on the slide here is really meant to provide an overview of how typical different types of buildings consume water. As you can see, heating and cooling can often count for more than 30% of facilities' overall water use. And then buildings with really high process loads like hospitals, laboratories, data centers, manufacturing sites, these require a lot of cooling and oftentimes have a really high resulting water usage. So while not all facilities have cooling towers, those that do tend to have really high water use, and there is therefore a significant opportunity to reduce that water use. So there's a variety of reasons to look into water efficiency in general, and more specifically related to mechanical systems. First and foremost, saving water can help reduce your operating costs. We're all trying to reduce that bottom line or improve that bottom line. And so water and sewer costs are really rising well above the consumer price index with really no signs of slowing down. So it's important to kind of get ahead of those cost increases. Secondly, saving water and energy can really help improve equipment efficiency, which often reduces maintenance costs and man hours that are required to maintain and repair equipment. Saving water can also save energy. There's this water energy nexus that really connects to the relationship of the energy required to pump, treat, and heat water, and on the opposite side, the water that's required to generate energy. So in your mechanical systems, reducing your heat load by making your equipment more energy efficient can also have quite a bit of water savings as well. This energy water nexus is a really important concept with mechanical systems overall. So by evaluating water and energy efficiency together will really provide you the best results and the greatest cost savings. And then lastly, saving water in your mechanical rooms really tends to be behind the scenes. Sometimes there's facility managers who are really hesitant to implement efficiency projects like restroom upgrades or landscape replacement based on this fear that building tenants or visitors won't like those equipment. But mechanical equipments can provide you with significant savings without really directly impacting your occupants. So one overarching thing we like to recommend for any facility before you really undertake a major water efficiency project is to call your utility. It might sound counterintuitive, but most water utilities really want to help you save water and can offer a range of services that can be immensely helpful. This can include providing you with historical water use data, offering expertise or assistance in conducting a water assessment. Sometimes utilities will even help you pay for it. Some utilities offer a deduction on wastewater rates for any water that's not sent to the sewer, such as water that's evaporated from a cooling tower or that's used outdoors for irrigation. Your utility will be able to better explain any metering or reporting requirements to earn this credit. Utilities can also communicate rebates and other incentives that they have for implementing water efficiency upgrades. They can help sign you up for leak alerts, particularly if you use some sort of advanced metering infrastructure. And then lastly, they may be able to point you to some preferred vendors to either conduct a water assessment or provide some other expertise in terms of saving water at your facility. I heard this on another WaterSense webinar from Anarchy Chamberlain. I really liked it, so I thought I'd share it here as well. It's kind of as a general approach, and especially when talking about expensive mechanical systems, it's beneficial to follow an efficiency hierarchy to help make water efficiency more manageable and cost effective. So the first step is to really make sure your equipment is running as intended and as designed. If you identify leaks or broken or malfunctioning equipment, you want to get that repaired as soon as possible. When dealing with sensors, valves, really any kind of pieces or parts of mechanical equipment, there's always a chance that those mechanical items will fail and get in the way of proper operations. So be sure to investigate and repair those whenever they come up. Second, once everything is working as intended, you should consider low and no cost adjustments to the systems to achieve water savings. Oftentimes, there may be easy opportunities just to make simple adjustments to the controls or the operating procedures of a system that don't require a major investment. To provide a cooling tower example, this might be adjusting your conductivity controller settings or working with your cooling tower vendor so that you can blow the system down less frequently while still operating within the acceptable range for the cooling tower. The third level of hierarchy is to then make sure that those processes are all routine. So making sure that your water management activities like monitoring water use or confirming operations are part of your regular routine as a facility manager or operator. That helps ensure that the equipment continues to operate efficiently on an ongoing basis. And then only after you've really conducted your repairs, made operational adjustments, improved your routines to operate your system efficiently, then you should consider those major capital upgrades. Upgrading your equipment is often where people want to start, but this can often be a major stumbling block because these major projects tend to be capital intensive. So while identifying things like alternative water sources or major technology upgrades can have very real water and energy savings benefits, it often ignores the fact that a lot of those savings may be possible just by optimizing your existing systems and your existing operations. So I'm now going to talk about some of the major areas of mechanical water use within commercial facilities. Water is commonly used as a heat transfer medium in various mechanical systems used for heating and cooling. This includes single pass cooling, chilled water systems, cooling towers, and steam boilers. We're focusing really on cooling towers today, but if you're interested in steam boilers, you can look at some of our previous webinars that we've done where we've touched on that topic. So single pass cooling, if present, has the potential to be the single greatest water waster in your facility. So when you're looking for areas to improve water efficiency, this is really the best place to start. So single pass cooling is a situation where city water is plumbed to a piece of equipment to remove heat. Typically, it's a motor or a compressor. After use, it goes right down the drain. In commercial facilities, you might find this associated with air conditioning systems, walk-in freezer, refrigerator, ice machines, vacuum pumps, some medical equipment. And this cooling method can really be really water intensive and can use 40 times more water than the same heat load removal that a cooling tower offers. So as a general best practice, it's best to just eliminate this wherever possible. You can do this by either replacing water-cooled equipment with air-cooled equipment or by providing cooling water from an existing chilled water loop. There's typically significant cost and water savings available for these changes. In cases where you can't eliminate it, make sure that you're using the absolute minimum water that's required to remove the heat load from the piece of equipment. Check your equipment specifications and make sure that you're getting that maximum temperature rise from the water that you're applying. And make sure that the flow of water turns off when the motor or the compressor is not running. This is often controlled with a solenoid valve. So, essentially the water will shut off when the motor or the compressor stops running. But these valves often fail. So this is a maintenance item they should pay attention to and periodically check in on them to make sure that the valves are really closing when they're supposed to. In some cases, this single pass cooling water could be reused for another purpose, but it's really best to just eliminate it altogether. And I'll show you some of the savings on the next slide. So here's a kind of photo representations of some of the single pass cooling savings. So on the left, you have water at about 1 gallon per minute, really not much more than a trickle. And with that, you're using 500,000 gallons of water per year, and it's going to cost your facility about $6,500 per year at average water rates. At the right, you have a 6 gallon per minute flow rate. If your water is flowing 24 hours a day, 7 days a week, you would be using more than 3 million gallons of water per year and almost $40,000. So you can see how replacing this equipment can have significant cost savings. So most facilities that do have substantial cooling loads use a recirculating chilled water system. I apologize. Some of my automation or the graphics on this got stripped out from WebEx, but I'll try to explain how these systems work. So chilled water systems have several key components. There's a heat exchange unit, which is at the bottom here, which is supplied with chilled water that's providing space cooling or sometimes equipment cooling. This is where the heat load is coming from. You then have the chilled water that takes the heat load and directs it back to the chiller. Typically, the chiller water loop is fully closed, so there should really not be any water use or loss from that system. It's good best practice to have makeup meters on the chilled water loop so that if you're seeing any consumption or continuous makeup, you can identify that you likely have a leak and get it resolved. The chiller unit is what generates the chilled water through the refrigeration process. The chiller transfers the heat from the chilled water loop to the condenser water loop, which is kind of in the middle here, that heat transfer. The condenser on the refrigeration cycle may be either air cooled or water cooled. Larger units tend to be water cooled using a cooling tower, which is shown here at the top. Water is then evaporated from the cooling tower, which then cools the condenser water and returns it back to the chiller to repeat the cycle over and over. We're not as concerned about air-cooled systems from a water efficiency perspective, so we're really going to focus the rest of this webinar on cooling towers. So again, unfortunately, some of my neat graphics got ripped out, but just to get everyone oriented, I want to just take a few moments to talk about some of the basics of cooling tower operation. They're fairly simple. So water and air flow past each other, typically in the counter current or cross flow configuration to provide cooling. So in this schematic, you have hot water from the chiller that's introduced at the top of the tower by spray nozzles, and these spray nozzles spray the water across the fill material while air is drawn up through the tower by a fan. As that air passes over the water, some of the water is evaporated, which then removes heat and reduces the temperature of the water in the cooling tower. The energy lost from this evaporation process is what helps remove the heat from the system. This cooled water is then returned to the chiller to collect more heat, and makeup water is added to the system, which I will talk about next. So the cooling tower has a number of inputs and outputs that explain how that water is being consumed in the system. First, you have the circulated cooling water that's introduced into the tower to be cooled. This water is removing heat from the piece of equipment, in this case the chiller, and it is returned to the chiller once it has been cooled from the tower. So that's a recirculating loop that goes through the tower and through the chiller. You then have some water that's evaporated to remove heat. That's that plume at the top of the cooling tower. This is all by design. That's the purpose of the cooling tower, so you want that evaporation to be happening. You might have some small quantity of water that's lost as droplets that spray from the tower. These are called drift. There's little blue dots that you see on the left there. Some water is also discharged as blowdown to keep minerals from building up in the recirculating cooling tower water. That's the brown arrow at the bottom. And then lastly, to replace all that water that's being lost from evaporation, drift, and blowdown, you have makeup water. So now that we kind of understand some of the inputs and outputs of a cooling tower system, we can understand really where the opportunities to save water are. The first option is looking at the evaporative heat load. Evaporation is the primary function of the cooling tower. Again, we want that to happen because that's what's carrying heat away from the system. Based on just the thermodynamic properties of water, it takes about 1.5 gallons of water per hour to need to be evaporated for every ton of cooling that is needed. And that number is fixed. Since we want that cooling to occur, evaporation is not really the focus of water efficiency. With that said, anything you can do to make your chiller plant more energy efficient will also lower your cooling load and thereby reduce the amount of water that needs to be evaporated. So aspects of your facility that may impact that evaporative load include your building design and envelope, HVAC equipment, lighting and plug loads, occupancy, operations and maintenance practices. Those can all impact the efficiency of your chiller plant and just the efficiency of your building. So therefore, things even like lighting retrofits can have a commensurate water savings because, as you replace lights with LEDs, you have a lower cooling load, which means a lower load on the cooling tower, which saves water. So as I mentioned, some water is lost due to drift and splash out. In a well-designed tower equipped with a drift eliminator, this should really be minimal. However, if you're noticing as you're doing facility inspections that there's visible droplets that are exiting the tower or water that's ponding on the roof or on the pavement, this may be an area where you want to pay attention and potentially replace your drift eliminators. If necessary, new drift eliminators can be added to existing towers or higher efficiency drift eliminators can be installed to replace old poor performing ones. These high efficiency drift eliminators do have other ancillary benefits as well, such as reducing risk of Legionella. Other maintenance item to be aware of, and this is probably one of the most important things to hear today, is pay attention to your cooling tower overflow. Almost all cooling towers are equipped with an overflow drain to prevent the tower from overfilling and potentially causing damage to the facility. Oftentimes there's like a level sensor or a fill valve that gets stuck, and once that fails, the water will continually run and run, and water will go into the overflow drain. So this is a photo on the slide from a tower basin where the fill valve controlling that makeup water was stuck partially open. Water was constantly flowing, overfilling the basin and going down the drain. So this is a good thing to check on just daily rounds. You should never ever see water going to the overflow drain. If there is one, it means your tower has a problem. And because makeup valves often flow at really high flow rates, if you don't notice this for a couple days, you can really be wasting hundreds of thousands of gallons. So it's really a great thing to check up on a daily basis. And yeah, correct that problem immediately if you see it happening. So beyond looking for overflow, the primary opportunity to improve water efficiency in your cooling tower is by reducing your blowdown by concentrating minerals in the recirculating water system. As the mineral concentration rises, the blowdown stream bleeds off a certain amount of it and replaces it with city water that has lower dissolved minerals, thus reducing the overall concentration of these minerals in the system. So mineral control and blowdown is necessary to protect your cooling tower. We don't want to ever say don't blow down your system. And it's necessary because it prevents formation of scale, corrosion, or biological control. The measure of efficiency that evaluates your tower and how it's operating in terms of makeup and blowdown is called cycles of concentration. This is the ratio of concentration of minerals in the blowdown water to the concentration of minerals in the makeup water. It also tends to be representative of the ratio of makeup volume to blowdown water. So the higher the cycles you are able to achieve in your tower, the less blowdown is occurring and the more water efficient your system is able to be. So if you recall on the slide I showed earlier, the cooling tower, the only water that's being added to a cooling tower is makeup water. When operating properly, the only significant ways that water should be leaving your cooling tower is through evaporation and blowdown. Drift and leaks should really be negligible. So reducing your cooling tower blowdown is the largest opportunity for water savings. As I mentioned, the reason for blowdown is to keep those minerals or dissolved solids from building up in the tower and causing scale. An example of that's really shown here. So the city water contains dissolved solids when it comes in. As the water evaporates, these solids stay in circulation and begin to get concentrated over time. If the concentration gets too high, the solids will begin to form scale on the surfaces of your chiller system or your cooling tower, which will then degrade performance and damage the equipment. There's some water that's regularly discharged. That's what we call the blowdown to keep these dissolved solids in check. So the blowdown is typically controlled by a conductivity meter or a controller. Careful blowdown control offers really the best opportunity for savings in a cooling tower system. I forgot to change the slide. Sorry about that. So that background really establishes the basis for saying that as you maximize your cycles of concentration and reduce blowdown, your system efficiency will improve. To maintain the high cycles of concentration, you want to keep the minerals in solution by managing the system's water chemistry. This is done by adding chemicals or another treatment mechanism that help control for pH and inhibit scale and corrosion. The target cycles of concentration that is achievable in your cooling tower is based primarily on your facility's incoming water quality. This table from ASHRAE 189.1 establishes maximum values for certain parameters that are within the recirculating cooling water that you should try to stay below. This information can help you identify your cycles of concentration limit. So for example, if you have a limiting parameter of total dissolved solids or TDS, you can identify your cycles by evaluating what that is in your incoming water quality. So if your incoming TDS is 1,000 ppm, your tower may only be able to safely run at about 2 cycles because 2,050 divided by 1,000 is approximately 2. However, if your incoming water has a TDS of 200, you should be able to achieve 10 cycles. So this is a really helpful table for just calculating your own maximum cycles that you can achieve. So calculating cycles of concentration and establishing a water treatment program may sound complicated, and it really is, and it can't be. That's why many facilities commonly contract this out to a water treatment vendor. This is usually someone who comes to your facility once every couple of weeks or every month and should be checking up on your water treatment program. They'll take measurements, they'll monitor chemicals to ensure that everything is in working order. When working with a vendor, there's some important things to keep in mind at the onset and throughout your relationship to ensure that you're achieving your goals. First, you'll want to communicate your goals with respect to water efficiency. We want to encourage you to work with with a qualified water treatment vendor that really shares your goal and understands your desire to achieve water efficiency. Oftentimes, these vendors will just kind of set a low cycles because they're being paid to make sure the tower gets maintained, and therefore it doesn't matter to them if they're using more water to do it. But by establishing your own, working with them to establish a target cycles of concentration that acknowledge your own water efficiency goals will, help ensure that you're getting the most out of your relationship with them. Second, ensure that once they're doing their service visits, that they're providing you with a comprehensive summary at the end of each one. This should include water chemistry information. Your treatment vendors should be taking regular samples of your incoming water quality and cooling tower water to help determine whether goals are being met. And if they aren't providing this kind of service visit summary, make sure to ask them for it. It is really kind of like the bare minimum of what they should be doing. Third, be sure that you're reviewing the service reports so that you can tell whether you're actually achieving your cycles of concentration goal that you've mutually established. Sometimes there's very valid reasons why these target cycles aren't being met, such as a mechanical failure or during equipment, ramp up at the beginning of the season. However, sometimes it's just a result of, the vendor not paying attention or not doing what you've hired them to do. So be sure to request and review these reports on a regular basis. And lastly, just find a vendor who can also be a partner in these water efficiency goals. Treatment vendors can be a very valuable asset when it comes to identifying other technology options that can be used to increase your cycles of concentration beyond what's achievable just with typical chemical treatment. So they can often advise on water softening or other mechanisms to improve your cycles. So this is a typical water treatment report that we can kind of see that they should leave behind. They can all kind of differ a little bit in format, but they all usually contain the same information. So the report includes conductivity of the makeup water and the cooling tower water. This cooling tower water is really the same as the blowdown water. Dividing the blowdown conductivity by the makeup conductivity gives us a little over 6 cycles, which isn't bad. One thing that you'll want to be aware of is to look at whether the conductivity sits where it sits with respect to the controlling point. So this tower has a control point of below 2750. We're right at the top of that, 2755. So that's where you want it to be. That ensures that the tower is operating as it's been set to operate. In terms of ways to improve cycles of concentration within your tower, first, if you don't have one, install an automatic controller that bases blowdown based on conductivity. This should help set these set points and maximize your cycles. Second, install makeup and blowdown water meters to also help you track your water use on an ongoing basis to monitor trends and take corrective actions as necessary. I mentioned this earlier, but one important cost savings measure is that with appropriate meters, some utilities will let you deduct the quantity of water you evaporate from your sewer bill. These savings can often be quite significant just because cooling towers use a lot of water and evaporate a lot of water. And these cost savings from sewer deductions can often be enough to offset some of that upfront cost that's needed to install meters or other control mechanisms. So definitely reach out to your utility to look into that. And then taking steps to improve your water quality, such as side stream filtration, basin cleaning to remove sediment, or water softening if your water hardness is a problem in your area. Those can also allow you strategies to improve your cycles of concentration. And as I just mentioned, your water treatment vendor can hopefully advise you on some of those options. This chart here shows the potential savings that you can achieve by increasing your cycles of concentration. Read from initial cycles on the left across the top to your new cycles, you can see that, for example, improving from 3 to 6 cycles would reduce your cooling tower water use by 20%. And this chart here shows that as your cycles increase, the amount of water that's used per day, this is just an example, 100-ton tower, also goes down. You should really be trying to achieve 6 or greater. The savings beyond that are kind of less significant, but obviously if you're able to achieve them, great, but targeting that 6 value or greater in terms of cycles will get you significant savings. I've kind of just covered a lot of information and best practices in a short amount of time. So I just wanted to take a minute and summarize some of the common failure points that we see that can lead to water waste or cooling tower damage. As far as mechanical issues, you can have a stuck makeup or blowdown valve. A makeup valve that's stuck open will continually fill and overflow the tower. A blowdown valve that is stuck open will continually drain water, essentially creating a single pass system, which will also waste cooling tower chemicals. A blowdown that is stuck closed will not be able to remove minerals from the system and can essentially lead to a scale event. Faulty sensors can also have similar repercussions. If the conductivity or the level sensor isn't communicating correctly with the controller or the blowdown valve, you could be blowing down too much or too little. Like any system, there's always potential for pumps to fail or pipes to leak. And then lastly, controllers, either for the conductivity or chemical feed system, can malfunction and again result in that tower blowing down too often or not enough. On the operational side, common failures include establishing incorrect set points at which the system should be blown down. Similarly, the level sensor in the tower can be installed incorrectly, leading to tower underfilling or overfilling. Lastly, the chemical feed system can be programmed incorrectly to apply too much or too few chemicals. Most of these can be easily identified and resolved by making sure that staff is assigned responsibility for the cooling tower. They don't need to be a mechanical engineer to understand what to look for during regular check-ins. So they should look for things like checking the overflow drain to make sure that there's no water flowing, monitoring and recording meter readings, and using them to calculate cycles, and looking at the conductivity meter to make sure the tower is operating at its set point. Another opportunity to reduce the amount of potable water used within your cooling tower system is to identify an alternative source of water that can be used to supplement replace city water that is in the makeup line. Some possible sources of makeup water include reclaimed wastewater, if your municipality offers it, rainwater, foundational drain water, and air conditioner condensate. One thing to remember when assessing these alternative water sources is that water quality, quantity, and availability should be considered. So only use alternative sources where they're able to really match the quality of the alternative source that's needed in the system. One good example of that is air handler condensate recovery. Air handler condensate projects are really an excellent source of makeup water for cooling towers, particularly if your facility is located in a hot, humid climate. Air handler condensate is water that forms on air handler cooling coils as it heats and conditions outside air. This water is typically just drained to the sewer or a storm sewer, but since it's generated in its highest quantity when the load on your cooling tower is highest, it makes a really excellent source of cold, clean water. These the biggest challenge for these condensate collection projects is typically the plumbing that's required to get the water from the air handlers to the cooling tower. However, if your pipe runs aren't too long or complicated, these can be really cost-effective projects. This picture just shows a few examples of some pretty simple designs. They do not need to be complicated. It really all it involves is a submersible pump, some PVC piping, and getting it over to the tower. So they don't need to be complicated. This is a map that is generated by the Federal Energy Management Program that they created to show where there's really good opportunity for condensate capture. As you can see, Southeast, Mid-Atlantic, Midwest all have really high potential for these types of projects. That being said, these projects can be effective really in any region, especially if your air handlers are in close proximity to your cooling towers. FEP also has maps related to rainwater collection and reclaimed wastewater availability, which are two other potential sources of cooling tower makeup water. The last thing I want to show is just a few facilities that I'm familiar with that have really focused on cooling tower improvements, air handler condensate projects, and these just kind of show generally the water savings that they've been able to achieve year over year by focusing on cooling towers. And with that, I want to hand it over to Scott Riley with St. Joseph's Health System, and he's going to talk about his healthcare system success in implementing some of these best practices and reducing facility water use. So, Scott.
Thank you, Robbie. Good afternoon. My name is Scott Riley. I'm the Director of Maintenance and Engineering for St. Joe's Healthcare System. This is a case study of a sewer and water reduction project that was implemented at two of our hospitals. Our organization consists of 3 main campuses and more than 40 off-site locations. The program we implemented was performed at our 2 largest facilities, which was in Wayne, New Jersey, and Paterson, New Jersey. As part of our mission, one of our commitments is to care for the environment. Additionally, from a financial aspect, the cost of water and sewer fees were steadily increased. At the 2 main campuses, we also had issues in the summer with water pressure. Sorry, I went too fast. In Wayne, the patient care bathrooms in the highest floors had a hard time flushing. The flushometers would get stuck, and the pressure on the main in the basement would go down to 30 psi. Sometimes the cooling tower makeup was so slow that on hot days we would have to turn the chillers off so the cooling tower could catch up and not run dry, which would affect the building temperature, of course. In Paterson, our cooling tower makeup issues and pressure loss were often associated with our consumption, because our consumption was so high, and the fact that the neighborhood kids would often open hydrants in the street in the summer. Compared to most industries, hospitals use a disproportionate amount of water. Healthcare being a 24-hour operation, and having old equipment often is the largest consumer of water in most cities. In the Northeast, sorry, energy efficient lights. In the Northeast, as you have in most areas, being one of the largest consumers of water becomes more relevant when you have a drought. Oftentimes, residents and businesses are contacted by the municipality to reduce water use. Being one of the largest consumers of water, I felt that it was our responsibility to police ourselves and to do our part to reduce the strain on the municipality. The first thing we had to look at was our annual consumption. When you finally figure that out, sometimes the number sounds normal. This is especially true when you look at pounds of steam an hour or decatherms of gas that you use a year. When you have a huge campus and the bills have been consistent for years, the annual number can sound plausible. After you decide that maybe your water use is higher than acceptable, you then need to figure out what areas you think you can attack. Some of your targets might seem easy and others might appear to be too much work, as they often require assistance from your internal staff. These 4 targets are huge consumers of water. Depending upon funding and manpower, can often take years to plan and budget for. Up on the left-hand corner, that's medical vacuum. The underneath that is water-cooled air conditioning system. To the right is an air handler, which produces a lot of water. And then the down the right bottom is actually it's a dish machine. Unless the water is repurposed for irrigation, water that is captured and recycled often is sent to the cooling tower. The reason for this is that condensation from air conditioning or city water can be reused in a cooling tower. Typically, the seasonal consumption of water in the cooling tower increases with the production of condensate that is ejected from the air handlers and the rooftop air conditioners. Another item of note is that your chemical vendor will be very happy when you start implementing these measures. The reduced city water makeup will reduce the amount of chemical that you use, and the reduced blowdown will allow the chemicals to be more efficient and kill bacteria. Dish machines typically use a lot of water. The dish pre-rinsing machine reuses rinse water and discharges a percentage of that to the sewer. By adding a dead man switch to the system makes it even more efficient when staff walk away. This shows the beginning of our water reduction in Wayne and some items we did in Patterson. Once-through water-cooled air conditioning is often found in older air conditioning systems. They typically are installed on equipment where the installation of a condenser to reject the heat is difficult to place or land. You know, walk-in boxes and kitchens and center core of buildings, morgues, and other air conditioning systems where you can't land a condenser as a few examples. These are some items of reductions that we started experiencing at each location. Wayne's reduction may not seem that dramatic, but the campus is smaller. This is a condensate tank that is normally used for steam condensate capture. This is what we typically use to capture condensate water from our air handlers, and then we pumped it from there into a cooling tower. As you can see by this graph, the reduction started becoming more substantial with the amount of implemented projects that we install. You can see in 2021, COVID steered our focus away from this project momentarily. Even when that happened and other priorities take place, the items you implemented saving water is year after year. At the end of 2023, you could see the total reductions that have been achieved. The achievement not only involves saving water and reducing sewer costs, but it also now maintains our city water pressure to be the same in the summer as it is in the winter because of our reduced use. The city actually sent our water meters out to be recalibrated because they thought that there was something wrong with the meters. This year, we installed a line under the parking lot so we could start sending water to some of our cooling towers that are not on the roof in the main building in these slides. That's all I got. Thank you very much.
Thank you, Scott. That's great. I like the part about the water utility reaching out to see if your meters are broken, because your water reduction is so dramatically reduced. So yeah, that was really good. I'm happy you were able to highlight some of those real world best practices. And I'm sure if there's folks who have questions about the case studies, feel free to type in the chat and we'll talk about them towards the end. Real quick, kind of in the vein of case studies, we wanted to open up a poll in case there's anyone on this call who is interested in potentially sharing your own water efficiency success on a future webinar. Kirsty mentioned a lot of the topics that we cover throughout the year, including restrooms, outdoor, water management, mechanical systems. So if you're interested in sharing a project or finding out more, certainly answer the poll and reach out afterwards. Give me a few minutes to go through. And while that goes on, I'm going to go through a few more slides before we open up to the Q&A. So WaterSense has a variety of other resources that can be helpful when it comes to cooling towers, other mechanical systems, or really any of your water management issues. We've developed many technical tools and resources to help with conducting a water assessment, creating a water balance, or understanding other water use or opportunities to improve water efficiency for a variety of different building types. We keep all of our resources for commercial facilities on our commercial tools and training section of our WaterSense website. You can see the URL there. This houses technical guidebooks, assessment tools, worksheets, checklists, case studies, as well as links to recorded and upcoming live trainings like this one here. A lot of the content from today's webinar is from WaterSense at Work. WaterSense at Work is our most comprehensive guidebook and provides really in-depth information regarding a lot of what was covered today, and just more broadly of really any type of water end use you can imagine your facility. It's focused on commercial industry facilities, and it gives instructions on how to understand, manage, and reduce your water use. It covers water management planning, water use monitoring, as well as specific fixtures and equipment like restroom equipment, commercial kitchen equipment, outdoor water use, mechanical systems, laboratory medical equipment, alternative water sources. It also includes a lot of helpful calculations and tips for creating a water balance. We're in the process of updating much of this guide. We're probably about 60% of the way through, so certainly stay tuned, but you know, even the old content still immensely helpful. The Environmental Defense Fund has also has this water management application or water map tool that's focused on cooling towers. It's an Excel-based spreadsheet with three primary components. There's a water scorecard, a water efficiency calculator, and a cycles of concentration calculator. The scorecard really helps facilities or companies assess their water efficiency, whereas the calculator estimates water and financial savings from cooling towers or free air cooling improvements. We didn't really talk too much today about free air cooling, but this is a concept where you're using outside air that is at low temperatures to assist with cooling loads from within the building. Using free cooling can reduce your facility's energy and water use. And then finally, the cycles of concentration calculator takes information about your water quality and estimates the recommended maximum cycles of concentration from your cooling tower. Another great resource that's available is from the General Services Administration through their Green Proving Grounds program. They evaluated a number of different alternative water treatment technologies for cooling towers to validate some of the vendor claims about those projects and savings opportunities. So GSA summarized their findings in this detailed report. So if you're interested in kind of alternative treatment technologies, whether it be non-chemical treatment or some other treatment mechanism for cooling towers, this is a really great report that can kind of find third-party validated feedback on some of those technologies. Some of them offered up to 50% savings in blown out, so they can really be significant. We covered a lot of information today, so real quick before we open up for questions, I just want to kind of summarize what you might be able to do right now if you're feeling anxious after this. First is to look for single pass cooling equipment and to make sure that it's set to use the minimum flow rate required for cooling in all instances, and also just start investigating alternatives for single pass cooling equipment. You'll also want to install and read meters on all your makeup water lines to your cooling towers, boilers, and chilled water systems, all blowdown water lines, and all condensate return lines. This just helps you monitor how much water is being used. Create a daily punch list or rounds checklist and assign it to a specific staff to make sure that they're monitoring the cooling tower, particularly the overflow drains, meters, and evaluating what the cycles of concentration are to make sure that the cooling tower is operating correctly. Next, contact your utility to see if they have any programs to offer in terms of saving water and money. This may also include sewer deduction credits, rebates, or other assessment support. Take a minute to try to track down those water chemistry reports from your water treatment vendor and take a look at them, see what kind of information is included, and try to understand what your cycles of concentration are. If your water chemistry allows, also reach out to that vendor to see if your cooling tower cycles can be improved, ideally to 6 or more. And lastly, again, if your air handlers are kind of nearby your cooling towers, or even not, it sounds like Scott kind of dug up their parking lot to get this done. There's ways to get water from one part of the site to another. So consider air handling and condensate projects. So with that, I'm going to open it up for questions. Percy, I think you are going to tee them up.
Yeah, cool. Well, first off, Robbie, Scott, thank you. I think we've got 6 minutes and I'm seeing 4 questions, so maybe a minute per question. The first one is, does it make sense to just eliminate cooling towers and focus on air-cooled units?
Well, WaterSense has historically been a voluntary program, so we're out here to promote water efficiency on a voluntary basis, and we are non-regulatory. So I guess I'll say I'll leave the regulations to regulators to decide whether to ban them entirely. But what I will say is that I think cooling towers has historically been used as a mechanism to achieve greater building energy efficiency and resulting cost savings. These days, water is getting much more expensive, and water and sewer rates kind of have continued to rise over the past 25 or 30 years faster than inflation. I think like 3 times as much as inflation. So as water rates continue to increase, that equation or that balance of when it makes sense to use a cooling tower versus when it makes sense to pursue an air-cooled system will really start tipping in the scales of looking at air cooled instead. So, certainly if you're interested in designing a new building, or if you're involved in the design of a new building, I would really take a hard look to evaluate the life cycle cost of operating a cooling tower versus operating an air cooled system, because it might surprise you that the cooling tower is much more expensive to operate.
All right, great. Scott, sorry, did you want to jump in on there?
Sure. With cooling towers as well, it depends on the size of your system. If you have 5,000 tons of cooling, 8,000 tons of cooling, you're probably going to be forced to go to a cooling tower. Possibly if you're under 100 tons or so, there's probably a tipping point to where you have to go one route or the other. But definitely long-term costs need to be factored in.
Okay. All right. Second question is there a filter in the blowdown that helps capture unwanted minerals? Maybe that's a system design question.
Generally, no. So you want the blowdown to take away all the unwanted minerals. Essentially, that blowdown is used to remove dissolved solids and other elements from the recirculating water. So you wouldn't necessarily want to filter that as it leaves. There are filters either on the makeup line, or they'll have like side stream filtration that'll help pull out some of those dissolved solids or suspended solids from the system as it operates. And so, I think the rule of thumbs generally try to capture about 5 or 10% of the recirculating water quantity within those side stream filters. And those can be effective at helping to improve efficiency and improve the water quality within the system to reduce things like scale or corrosion.
All right, I think we've got 2 more minutes
as well. Sorry.
Yeah, you could actually use a water softener for your cooling towers.
Yeah, water softener as well for incoming water. Yeah.
You could soften the water, but then you're going to have to regenerate your water softeners with salt. So there's costs associated with that as well.
All right, so I think we've got 2 more minutes. Let's get to one more question, and the ones that we didn't get to, I think we'll do a follow-up offline. Last question is, how do you calculate cycles of concentration if you have a treatment system that reduces TDS? So I think that might kind of change the traditional equation for cycles of concentration.
Yeah, so instead of taking your sample of your city water, you would just take the sample of the water that's coming out of that treatment system. And your cooling tower vendor should be able to assist with that. And yeah, you would essentially calculate, let's say your city water has a TDS of 500 and you are able to treat it so that it only has a TDS of 200. That you should be able to then base your cycles of concentration off that 200 number, because that's the water that's really going into your tower. So yeah, the equation would be the same for cycles of concentration, but you'll just consider that you're starting with better quality water than you would have otherwise.
All right, well, in our last minute, once again, thank you, Robbie, Scott, Chris. Thanks to our audience for sticking with us for the whole hour. I want to remind everyone, please tune in for our last 2 webinars of the year. Also, I think at the end of the webinar, you'll probably get a survey. If you can, take a moment to fill that out. It actually really does help us and helps to kind of continue our operations here. And with that, hope everyone has a great rest of the week.
Thank you. Bye, everyone.
Thank you.